We're very happy, I should say, to have Professor Nishimori today joining us in giving this first talk of the day. He studied at the Department of Physics of the University of Tokyo, and after obtaining his PhD, he spent some time as a postdoc at Carnegie Mellon and at Rutgers University in the United States. He then returned to Japan, where he joined the faculty of the physics department at Tokyo Institute of Technology. And more recently, he moved to the Institute of Innovative Research, where he leads the quantum computing research unit. He specializes in quantum annealing and physics of disordered systems. And in fact, today he will tell us about quantum simulation by quantum annealing. And before starting, I want to say one more thing. We're very happy to have Hiritoshi here today. And there's a special thanks that I want to give him because he is joining us directly from Japan, where it's very late at night. And so we very much appreciate it. And so without further ado, please go ahead and take it away. Thank you very much.
Thank you for the kind introduction. I'm Hidetoshi Nishimori, as he introduced, from Tokyo Institute of Technology in Japan. 11 p.m. here, but that's okay. It's just for a single night. So I will today talk about an application of quantum annealing to quantum simulation. So first, I will give you a brief introduction to quantum annealing in general. The concept of quantum annealing that we proposed back in 1998 was to solve the ground state search problem of the Ising model with generally complicated interactions. And here, as you see in this cartoon, there are many Ising spin configurations there, 2 to the n of them, exponentially many configurations, where n is the number of spins or number of sites, and the energy is a function of these configurations. And if the interaction of the Ising model is very complicated, then this energy landscape is also complicated. So to find typically the spin-glass problem, and to find the ground state, the lowest energy state in this complicated energy landscape is a difficult problem. NP hard problem in the language of computer science. And indeed, this ground state search of the Ising model is known to be equivalent to solving combinatorial optimization problems. And this latter set of problems, combinatorial optimization, is very important in a real life. So this is important in physics as well as for the society at large. And of course, there are many methods to solve this problem, but quantum annealing uses quantum fluctuations to search the best solution among very many states. As you see in this Hamiltonian for the transverse field Ising model, we introduced the sigma x term, this term, in addition to the Ising model, which is represented by sigma z, by linear form of sigma z's. And we first set the coefficient of the transverse field to a finite value, a of 0. S is the time parameter running from 0 to 1. So initially, only this term, the first term, exists. And the ground state of this term is trivial because it is a summation of sigma I x and independence. So the system is independent, a collection of independent spins or qubits. So the ground state is just a product state in which all spins or qubits are pointing to the plus x direction. So let's start from this trivial ground state, which is easy to prepare on the device. And let's reduce the amplitude of the first term to 0. And simultaneously, we increased the amplitude of the Ising term from 0 to a finite value. Then at the end of the day, you will have this Hamiltonian, the Ising Hamiltonian, for which we want to find the ground state. And if we change those coefficients slowly enough, then the adiabatic theorem of quantum mechanics guarantees that the system state will stay very close to the instantaneous ground state at each S. The system traces almost exactly the instantaneous ground state from H0 to H1. So this trivial ground state is gradually changed to the final non-trivial ground state. So this is the basic concept of quantum annealing. And there are many studies about this strategy. But I will introduce a different way to use quantum annealing, that is quantum simulation. That is, since we have a real qubit, a real chip composed of superconducting chips, superconducting qubits produced by the wave systems, we can run experiments of quantum systems represented by the transverse field Ising model, and see how the theory developed for this system is realized on the chip. So this is a real experiment. And I will focus myself to this latter aspect of quantum annealing. And this field is relatively new, but a relatively large number of studies have been carried out on this aspect of quantum annealing. There are two types of studies of quantum simulation by quantum annealing. One is for the static or equilibrium properties, and the other is about the dynamical or non-equilibrium properties. And the first category includes, for instance, the spin glass problem in 3 dimensions, the Koster-Thalles transition, spin ice problem, the Shastry-Sutherland model, field theory, and the Griffiths-McCoy singularity. And I will introduce those two, the Koster-Thalles transition and the Shastry-Sutherland model, briefly later. And I will also introduce our own study of the Griffiths-McCoy singularity. And about the dynamical non-equilibrium properties, so far, most studies have concentrated on the so-called Kibble-Zurek mechanism. And I will explain how we realized quantum simulation on this problem in our recent work. So first, I will review the study by Andrew King and co-workers on quantum simulation of the Koster-Thalles transition. As probably many of you know, the Koster-Thalles transition is a prototypical topological phase transition in 2 dimensions. On the 2-dimensional lattice, there exist XY spins which can point to continuous directions on the plane. And those XY spins interact with each other by ferromagnetic interactions. So those points tend to point in the same directions. And in the ground state, the perfect ferromagnetic state in which all spins point to the same direction is realized. But as temperature comes into play or quantum fluctuations come into play, this perfectly ordered state is disturbed, and the perfect ferromagnetic order is replaced by the so-called quasi-long-range order, in which the correlation function between 2 faraway spins decay by a power law. And at very high temperatures, this quasi-long-range order is destroyed. And this low temperature ordered phase, quasi-long-range order phase, there exist pairs of vortex and anti-vortex. Those pairs exist exactly in pairs. That is, if there is a vortex, then there should be another anti-vortex nearby. And those pairs, this pair of vortex and anti-vortex cancel their effect each other. And if we look at the state as a whole, the quasi-long-range order is not destroyed. But as temperature is raised or quantum fluctuations become large, then these pairs dissociate and quasi-long-range order is destroyed and the paramagnetic state is realized. So this is a very brief introduction to the Koster-Thalles phase transition. And Andrew King and co-workers studied this Koster-Thalles transition on the superconducting qubit chip. And since this is a continuous system, continuous degree of freedom, one should devise a method to realize such a continuous degree of freedom by the Ising model. And they invented a very ingenious way to do so. And they placed Ising spins at the corners, at the edge, at the vertices of the triangular lattice. And following the configuration of spins at the three corners of a single triangle, they placed an arrow in some direction, depending on the configuration of three spins. And it turns out these arrows can have 6 possible directions, which is called the Z6 model. So this is a discrete version of the XY model, in which the direction of a spin is restricted to 6 possible ways. But it is known at a finite temperature or a finite quantum fluctuation, this discreteness is erased by fluctuations, and the system behaves effectively as a continuous spin system. So in this sense, the Koster-Thalles transition of the continuous spin system may be realized. So they tune the parameters, the temperature of the quantum fluctuation ingeniously such that the system can lie in the Koster-Thalles transition. This phase diagram has been obtained by classical simulations. This axis represents quantum fluctuation, and this axis represents thermal fluctuation. And they tune the parameter such that the system, the real superconducting qubit system, traces part of the Koster-Thalles phase. And the result of the correlation function is described here. This is a log-log plot of the correlation function as a function of the distance between two positions. So these straight lines represent a power decay. So if one tunes the parameters here, then this power decay or the quasi-long range order has been confirmed to exist. And away from those points, the system is in the paramagnetic phase, which is confirmed also by the exponential decay. So in this way, they observed the Koster-Thalles phase transition on the superconducting chip. This is the first case in which Koster-Thalles transition was observed by quantum simulation on the superconducting qubit chip. Our next example is the Shastri-Sutherland model, studied by Keris and co-workers recently. And this Shastri-Sutherland model is a two-dimensional frustrated Ising model in which there are two types of interactions, J1 and J2. And by choosing the appropriate size and strength of those two interaction strengths, the system becomes frustrated. That is, it is not easy to find the ground state. And the Shastri-Sutherland model also has this external field term. And this model has been studied theoretically by many people. First by Shastri and Sutherland, and they obtained this result this axis represents the strength of this field. And this axis is the magnetization in the Z direction. And these black lines represent the theoretical prediction for the infinite size limit at 0 temperature. So for low magnetic field, the system is in the antiferromagnetic state. And for very strong external field, the system is in the ferromagnetic state. And for intermediate values of the field, system is in the so-called plateau state, in which the magnetization is a third of the full value of the magnetization. And they studied this model. Keris and co-workers studied this model on the superconducting qubit chip and found those blue points. Of course, this system they studied has a finite size, and the temperature is low, but not 0. The temperature on the chip lies between 10 millikelvin and 20 millikelvin, so it is finite. So they didn't find this sharp step-like structure of the magnetization, but they found a clear indication of some anomaly around here and there. So they plotted those anomalous points on the phase diagram, drawn in terms of the field and ratio of two interactions, J2 over J1. And the results are plotted as red crosses here and there, which agree very well with the theoretical prediction drawn in the white lines. So in this way, they confirmed the phase diagram and the plateau structure of the magnetization of the Shastri-Sutherland model by quantum simulation on the superconducting qubit chip. So these are two recent interesting examples of quantum simulation by quantum annealing. So we made some contribution to this aspect of quantum simulation relatively recently using the Kibble-Zurek mechanism. So let me introduce the Kibble-Zurek mechanism briefly in the context of the classical two-dimensional Ising model. So at very high temperatures, the system is disordered, paramagnetic state. A black dot represents a spin down state and white dot represents spin up state. So they are very much mixed in the state, in the system. At a very low temperature, the system is ferromagnetic. So almost all spins are in the down state, for example, and their finite size ions of up spins if the temperature is not 0. And at the critical temperature, those states are mixed and there appear small and large ions of white spins in the sea of black spins. And at high temperature and at low temperature, the correlation lengths are short. The correlation lengths are, for instance, the size of those white ions. But at the critical point, the correlation length is very large. It extends from a very small value to a very large value. So reflecting this very long correlation length around the critical point, the relaxation time is very long because it takes a very long time for the system to flip those large ions. So this description is about the equilibrium state. But if we drive the temperature relatively quickly, then the system cannot stay in the instantaneous equilibrium state. So even if we set the temperature finally 0, if we drive the temperature at a finite rate, then the system will not be in the perfectly ferromagnetic state. And there should appear those small ions even at 0 temperature, which is a dynamical effect. So the problem is how many imperfections or those white islands will be created at the end of the process as a function of the rate of temperature decrease. And Kibler and Zulek answer this problem, answer this question. Let me explain the idea and the context of the transverse field Ising model in one dimension, which we studied by quantum simulation. So instead of the temperature, we have the transverse field, which represents the quantum fluctuation. So initially, we set gamma, the amplitude of the quantum term, very large. So the system is in the quantum paramagnetic state in which all possible spin configurations appear with same probability in the quantum mechanical sense. And if we set gamma equal to 0, then we have the Ising model. So the system will be a linear combination of all up state and all down state. But if we change gamma over j at a finite speed, then the system will go out of equilibrium. The process is diabatic. And the defects or the kinks between domains will be created even if we set gamma equal to 0 at the final time. So the problem is how many defects are created as a function of the annealing time. Intuitively, if TA, the annealing time, is infinite, then the system will stay in the instantaneous ground state by the adiabatic theorem. So n will be 0 for T infinity. And generally, n will be a decreasing function of TA. And the answer of Kibler and Zulek is as follows. The number of defects divided by the system size, that is the density of defects, is proportional to the annealing time TA to the power minus d nu over 1 plus nu z, where d is the system dimension, which is 1 in the present case. Nu is the critical exponent of correlation function, which characterizes the rate of divergence of correlation at the critical point. And z is the so-called dynamical critical exponent, which characterizes the rate of divergence of the correlation of the relaxation time. And in the case of the one-dimensional transverse field Ising model, it is known that nu and z are both equal to 1. So this exponent will be 1, will be 1/2, 0.5 in one dimension. But this is about our isolated system without interaction with the environment. But it is known from simulations that if we introduce interactions with the external environment represented by those bosons, bosonic fields, then these exponents will be changed from 1 to 0.6 or 1 to 1.98. So if we plug those values into this formula, then we have this value, 0.28. So we studied this problem on the chip to see if the reality is closer to 0.5 or 0.28 on the chip on the D-Wave machine. So here is the result. We use two machines. One is at the NASA Ames Research Center, and the other is at Barnaby at the headquarters of the D-Wave systems. And this is a log-log plot of the density of kinks, or the number of kinks as a function of the annealing time. So those straight lines mean a power law. And for small system size at 50, the power is different from other chain length because this value, the data for this value don't satisfy the condition for the Kibler-Zulek theory to be valid. In short, the number of kinks is too small for the Kibler-Zulek theory to be valid. So we just took those large system sizes from 200 to 800 to analyze the data. So as I said, the theory for the isolated system without interaction with the environment predicts that the exponent should be 0.5, whereas the theory for system with interaction with bosonic environment predicts that the exponent should be 0.28. And the experimental values are here. On the NASA machine, it's 0.20, and on the Barnaby machine, the exponent is 0.34. So which theory is closer to the experiment? Well, 0.5 is definitely excluded, I should say. But there are deviations between 0.20 and 0.28, and between 0.34 and 0.28. But we claim that these differences between the theory for the system with interaction with the environment and the experimental values are non-universal, in the sense that it depends on the system. It depends on the chip we did experiment. It should reflect some non-universal factors, such as the degree of disorder, imperfections in the chip, which depends on the system. But we are interested in the universal feature of the problem. So we judge that the reality is closer to this theory on the left-hand side. That is, the chip on the D-Wave machine interacts with the environment in this manner. And this result is about the average number of defects or kinks. But each single point on this experimental result represents the average of the number of kinks over 200,000 samples. It's a very large sample. So each point has a distribution of the number of kinks indeed, as you see here. And there is a theory by Adolf Del Campo that the cumulants obey a very interesting property for this Kibble-Zilek mechanism. That is, the ratio of the second cumulant, which is the variance, to the first cumulant, which is the mean, is a constant as a function of annealing time TA. As I said in the previous slide, the average of the number of kinks, kappa 1, is a decaying function of TA to the power of minus 0.28. But if we take this ratio, it becomes a constant. This is a surprising result with a universal value of 0.59. And he also predicts for the isolated system that the third cumulant, kappa 3, to the first cumulant is also constant with the value 0.13. And our experimental values are plotted here with the error bars. So clearly, the experimental values agree with the theory within error bars. So we confirmed his theory. But as I said, this theory is for the isolated system, whereas we confirmed that the qubits interact with the environment. So this means that quantum simulation experiment on the quantum chip predicts that the theoretical prediction for the isolated system should remain valid even under the bosonic environment. So this experimental result prompts the development of a theory for systems with interaction with the environment. Another contribution that we made on quantum simulation by quantum annealing is about the Griffiths-McCoy singularity. So let me review the concept of the classical Griffith singularity. it's about the Ising model with ferromagnetic interactions, but diluted. That is, some spins are removed from the two-dimensional plane. So there exist clusters of finite size, or sometimes very large sizes. And by reflecting this dilution, the critical temperature below which magnetization exists becomes lower than the critical temperature for the non-random, non-diluted system. But Bob Griffiths predicted in 1964 that even in this region between the critical point for this diluted system and the critical point for the non-diluted system, the system is not perfectly ferromagnetic in the sense that the magnetic susceptibility as a function of the external field has an essential singularity at H0. So although there does not exist spontaneous magnetization here, in this sense it is paramagnetic, but the system shows a very peculiar singularity. Intuitively, this is relatively easy to understand. There exist very large clusters, almost infinite clusters, even if we introduce dilution, although the probability of the existence of such large clusters is very small. But since the system is below the critical point of the pure ferromagnetic, non-diluted ferromagnetic Ising model, those large clusters respond very strongly to the external field. So this very large response of the system in very rare clusters produce this essential singularity as a function of the external field. So this is the Griffiths singularity of the classical Ising model. But the Griffiths-McCoy singularity is about the quantum system. And it is known that quantum fluctuations enhance this Griffiths singularity to the level that the nonlinear susceptibility even diverges in this range of the parameter. So we try to confirm this prediction, theoretical prediction, on the qubit chip by diluting interactions on the so-called chimera graph realized on the D-wave chip. So as I said, the nonlinear susceptibility, which is the third derivative of the magnetization, diverges, is predicted to diverge in a certain range of the parameter. So to confirm this prediction, we looked at the distribution of this nonlinear susceptibility. This is a random system, so according to the choice of the randomness, this has a distribution. And it is known that the distribution has a power tail for large nonlinear susceptibility. And if this exponent in the power is less than 1, or if this expression d over z prime is less than 3, then this the average nonlinear susceptibility diverges. So we look at the distribution function of this nonlinear susceptibility to see if this exponent satisfies this condition near the critical point. And this data, this set of data points suggests that indeed near the critical point is here, near the critical point, the exponent becomes 3 or lower. In this sense, we have evidence that the system behaves as the Griffiths-McCoy singularity theory predicts. So these are our contributions. So to summarize, the dynamical phenomenon of the Kibble-Zülike mechanism has been studied by quantum simulation on superconducting chips. And we have observed environmental effects by looking at exponents. And recently, people from D-Wave carried out similar quantum simulations inspired by our work, and they carried out very short annealing time experiments. And they found evidence that the Kibble-Zurek exponent for an isolated system is realized for very short times, which means that the noise of the environment come into play at the later process of the annealing. But this work is still unpublished, and we are discussing very vigorously with them. And we also carried out quantum simulation on the Griffiths-McCoy singularity. And we have evidence that nonlinear susceptibility is likely to diverge even in the paramagnetic phase. So these results of ours and others would motivate further quantum simulation by quantum annealing in the near future. Thank you very much for your attention.
Thank you very much for this very interesting and nice talk. I give you a hand for all of us. So we are now entering the question and answer session part of this talk. So please, I would say we have a relatively small group, 40 people, so you can just unmute yourself and ask questions if you like. Maybe let me simply start here. So I would like to come back to the Kibble-Zurek exponent. So it seems that the NASA machine had a smaller uncertainty also, not only a smaller result, but also a smaller uncertainty than the Burnaby machine. So would one say the total difference here between these two exponents is systematic uncertainty, or?
Well, yeah, hard to say, but as you point out, the error bars are smaller for the NASA machine, but the absolute value is larger.
Mm-hmm.
So the signal is mixed. The absolute value is larger means that more defects have been created, which means larger disorder.
Mm-hmm.
So I'm not sure if the NASA machine is better in that sense. The statistics doesn't mean something by itself. Well, I'm not very clear, but I cannot say more. The machine at Barnaby, the headquarters of D-Wave, is claimed to be a low noise machine by Beta Engineering in the same series. So that is reflected in the smaller number of defects, smaller number, smaller density. But
I see, okay. So then this maybe is also then just a nice quality check on these machines.
Yes, another factor is that those lower values in this log scale enhance the visual scale of error bars.
Right.
So I should look at the numerical data very precisely. You see, this range of error bars for the largest TA is about 10 to the minus 3, twice of the 10 to the minus 3. But this error bar looks larger.
Oh, right.
The scale is,
yeah. Thank you for clarifying. More comments or questions? Then maybe, so let me then continue maybe for a moment here. So what are the prospects of going to or simulating three-dimensional systems?
That is possible. That is possible. Three-dimensional system can be embedded on the two-dimensional lattice. That has been done indeed by the group of researchers at D-Wave. This first paper by Richard Harris and co-workers. They studied the spin glass problem in 3 dimensions and found evidence of the existence of the spin glass phase.
I see, okay.
But the system size is not very large because of the limit of the size of the chip, about 5,000 qubits.
I see, okay. Thank you. Christian, please go ahead.
Yes, so yes, I have a question about the model that you are using to model the coupling to the environment. So you use a particular model to get that exponent of 0.28.
All right, yeah.
My question is first, how realistic is that model? And second, if you know what are the hypotheses that you need to change on the model to get a different exponent?
Yes, if we introduce different model, the exponent may be different. For instance, if we introduce sigma x here instead of sigma z, the exponent becomes different. But we believe that this sigma iz is closer to the real situation in the real chip.
And why is that?
Well, this. What does this bosonic field mean? It means it is believed that it means the fluctuation of the superconducting current. It is not uniform perfectly. It fluctuates on the chip. It is flux qubit. It is not perfect. And these fluctuations, if small, can be represented by harmonic oscillator, of course, because around the stable state, it is always harmonic. Fluctuation is always harmonic. And this harmonic oscillation of superconducting current couples to some type of qubit behavior in terms of the sigma z component. Sigma x represent different type of interaction with the environment, which is not believed to be realized very strongly in the real chip. It is a long story, but in short, the conclusion is like that. So this is believed to be a closer model than others. It is not perfect, but it is believed to be closer to the reality on the chip.
I see. Thank you.
Dean Lee, please go ahead.
Thank you very much for the interesting talk. I don't know so much about D-Wave and the quantum annealers, so can you talk a little bit about the errors that are induced by these simulations? So you are doing the annealing process. About how much error, what is the equivalent fidelity if I'm thinking in terms of digital gates here?
Errors. Well, there are many sources of error. For instance, as I said, qubits are not produced almost, all qubits are not produced equivalently as theory predicts. They are different from one to the other. This causes disorder, which is not taken into account in this Hamiltonian represented here. So this should be a non-universal effect that I mentioned. And also the interaction between qubits, which we write J here, is not perfectly realized. This interaction may be different from one to the other due to imperfections in the manufacturing process. And this type of interaction is not directly realized in the gate model chip. It is not necessary. So this is a big difference. And another difference from the gate model chip is we continuously tune the parameters as a function of time.
Mm-hmm.
So this tuning of the parameter, which I wrote somewhere at the beginning, is ideally adiabatic, very slow, such that the system traces the instantaneous ground state. But it is done in a finite time, typically a microsecond.
Yeah.
The system is excited
So
out of the,
perhaps I can ask my question this way then. Suppose we had just a 2-qubit system, an Ising model, and you wanted to prepare the ground state of that Ising to just a 2-qubit system using the transverse field with quantum annealing, and you take as much time as possible. How accurately could you reproduce the ground state? To what fidelity could you reproduce the ground state?
theoretically or experimentally?
Experimentally.
If the number of qubits is 2, the ground state will be realized almost 100%, I believe.
Okay.
In the scale of 1 microsecond.
Okay, but so are you talking about 0.1% error? Or are you talking about 0.01% error? Or are you talking about 1% error?
Less than 0.1%, I would say. If the number of qubits is 2, it is easy. But our system in this experiment has up to 800 qubits, so it is very difficult. Difficulty increases exponentially. But
Okay.
2 or 3 qubits or up to 10 qubits, the system will trace instantaneous ground state almost exactly, I believe.
Okay, but something on the order of 0.1% error per. So for the 2-qubit case, so probably for the 4-qubit case, you have a loss of a little bit more, and then it exponentially increases, probably, right?
Yeah, that's right.
Okay, thank you.
Is it possible? Is it possible to make a sort of finite size scaling analysis by taking, say, half of the machine and then the full machine, and then comparing the two?
Well, as long as the Kibble-Zurich mechanism experiment is concerned, all data except for the 50 qubit system lie on almost on the same curve. So these data points for larger system size represent the infinite size limit, we believe. No scaling is necessary. 200 is large enough.
I see. Yeah.
More comments or questions? If not, okay, so let us all thank Professor Nishimori again for this wonderful talk and questions. And we have about 10 more minutes.
Thank you.
We have about 10 more minutes before the next presentation starts.